Yes, class. So in the last class, we had completed with the circuits, and now we are left with LC oscillations and transformers. So firstly, we'll start with LC oscillations. So from the term only, from this term LC, L means inductor, C means capacitor. So let's first discuss what is meant by LC oscillations. Now, oscillations are the same oscillations that you have studied in your earlier class, that is your class 11th. In the end of class 11th, you must have studied oscillation, waves and oscillations. So oscillations, definitions, oscillations, criteria, all these things remain the same here as well. But what is meant by LC oscillations? Definitely this name suggests that there's an inductor and there's a capacitor. So there will be an inductor and a capacitor. Now here what happens? The inductance is L, capacitance is C, right? So this shows what? This shows that a capacitor is there, and let's say the initial charge is Q naught. It is connected to an ideal inductor. So electrical energy that is stored in this charged capacitor. See, Q is there, it means this is charged. Let's say this is a positive plate, this is the negative plate. So this shows that this is completely charged. Fine, class. So from here what happens? Electrical energy stored in the capacitor is what? Electrical energy stored in the capacitor is that what we have studied in the last class also. I think we have revised the energy of inductor and capacitor. This is half Q naught square divided by C. Whereas right now the energy of the inductor, there is no current flowing within the circuit. So there is no magnetic field producing. Since there is no magnetic field producing, there is no magnetic energy associated. But as there is no current in the circuit, energy stored in the magnetic field of the inductor is zero. So right now what is happening? If I mark this as energy of the magnetic field, energy of the electric field, that is the electric energy. Right now, electric energy is high and magnetic field energy is zero. Fine. So this is the first one. Now let's see what happens next. Now what will happen as the circuit is now closed? Capacitor begins to discharge itself. I'll draw the circuit. These are the two parallel plates of capacitor, positive. This is the negative side. Now capacitor has begun to discharge itself. So if initial certain amount of charge that was present, now it will get lowered. Obviously it will get lowered because there is some dissipation of the charges. And now what is happening? Since charges are now moving, so current is there in our circuit now. There is a current. It causes the current because capacitor begins to discharge itself through the inductor. So it causes the current I. Now as the current increases, as this current builds up, it increases. What happens? There is a magnetic field around the inductor. There is a certain slight magnetic field around the inductor. This is why this is all because of presence of the charges that are flowing. And due to this current, what have we studied in EMI? As current changes, there is a change in the magnetic flux. That was the property, I think, and the principle of self-induction also. It was based on EMI. So whenever the current will change, magnetic flux will change, magnetic field will change. So here the same thing is happening. All right, so now if I talk about magnetic energy and electrical energy, there will be a little lesser of electrical energy and slightly increase in the magnetic energy. This was zero and this was high. Now electrical energy is now 0 and magnetic energy has now increased. And magnetic energy is what right now? This is half Li square. This is what we have studied already. We have done the derivation of this as well. Now, continuing with the story, what happens next? Now what happens is at a later instant, capacitor gets fully discharged. Means all the charges that were present within the capacitor now have gone out of this capacitor, because capacitor initially started discharge. It's like if you have a bottle full of water. If you will keep on emptying small portions of water, small spoons of water, small sips of water, if you drink, at then what happens? Your bottle becomes completely empty. The fact lying behind this is what? It's just that whatever thing is present inside the content, that is completely not present now. So capacitor is now fully discharged. Regarding the magnetic field, since there is high amount of current present in the circuit, amount of magnetic field lines that will be present within the circuit, this will also be high now. Why will it be high? Because there's a lot of current present and a lot of magnetic field that has been generated. These red lines are nothing but the magnetic fields. Now what happens to the energy status? Now magnetic field is completely high and electrical energy is totally 0. Got it? Till here is the step. This is the half part of the story. In the half part, we have studied how the high electrical energy got changed into low electrical energy, 0 electrical energy, and how from 0 magnetic energy, it has increased up to a certain level. Fine. Now what happens? Half Li square is there, that's the maximum value of high Li square. So entire electrostatic energy of the capacitor has been converted into the magnetic field energy of the inductor. Now after the discharge of the capacitor is completed, now what? This we have understood. Yes, the whole charge from the capacitor has been released out. It is discharged now. Now what will happen next? So see, after the discharge of the capacitor is completed, magnetic flux linked with the inductor also decreases. There is a certain magnetic flux linked with the inductor that will also decrease. As a result, what will happen? According to Lenz's law, even if you apply, or if you just say directly, what will happen? There will be a decrement in the magnitude of the magnetic field. So it charges the capacitor in the opposite direction. It means this time this will be the positive plate and this will be the negative plate. Yes, good evening, Zed. So now in opposite direction, charges will begin to charge the capacitor. This is inductor. Now reverse phenomena is occurring. So what happens to the strength of this magnetic field? The strength has now again decreased, but it is not 0 this time, because slight amount of magnetic field has been lost by it. After the discharge of capacitor was completed, magnetic flux that was linked with the inductor, this changed. Once this got changed, it decreases basically. Change in the sense what? It decreased. That was the change that occurred. Fine. So the current then persists through the decreasing magnitude, charges the capacitor, but in the opposite direction. See, remember initially when we started, capacitors above plate was positive and below plate was negative. Right now it is reverse of it. So you have magnetic energy, you have electric energy. If you notice, you're reaching the previous step back where both these energies are having slight certain values, where E will be equal to half Q naught square divided by C, and magnetic field will be equal to half Li square. Now what will happen? Again, all the magnetic field will become 0 and capacitor gets fully recharged this time. This process continues till when? The capacitor is fully charged now. This is again your inductor, this is your capacitor. So this process has repeated till the capacitor has become fully charged. This is now fully charged. No more changes can occur. Here, what will be the case? Magnetic field will again be 0, electric field will be again high. Right? There's no presence of magnetic field. Again, this E value will be half Q naught square divided by C. Now what will happen? Again, this will begin to discharge. So when now the phenomena will occur, what will happen? When this will discharge, magnetic field will occur. Then when it will begin to recharge itself, it will again shift the plate in opposite direction. So it will stop at this stage when the polarity of the plate has been reversed. That's why from here the process is not stopped. Circuit eventually returns to the initial state. This is not your initial state. Here the above plate is negative and the plate below it is positive. But when we started, it was positive and negative. So what happens over here? It will again begin the same phenomena, and when the polarity will change, it will give you the initial state back. That is now what is happening over here. There is oscillation of the electrical and magnetic energy, if you see. You notice there's oscillation of electrical and magnetic energy. At certain points, electrical energy is high. At certain points, magnetic energy is high. So this shifting of them, the shifting of the electrical energy and magnetic field, this is what is here referred to as oscillations. Charge capacitor is there, that's why we have C, and then inductor is there, that's why we have L. So LC oscillations are, these are basically qualitative explanation for the production of your inductors you have. I'll write down the definition. I'll tell you the definition of LC oscillation. Then I'll repeat all the steps one more. Wherever you're not able to understand, ask. So since the circuit eventually returns to its initial state, that's why we say these are oscillations. There's an oscillation that you will observe between the magnetic energy and the electric energy. So LC oscillations are what? And in the question also, you can be asked, what are LC oscillations? Explain qualitatively how these oscillations are produced. So you have to show these diagrams just in case if it comes for a marker which is more than 2. So this says what? When a charged capacitor, this is basically when a charged capacitor, this is when a charged capacitor, this is allowed to discharge. This is what we had seen when a charged capacitor is allowed to discharge. This is only what we had seen. All the charges were moving out. So now what happens? Through what? Through an inductor also. This is also important. Through a non-resistive inductor. Through a non-resistive inductors, what happens? Electrical oscillations. Electrical oscillations of constant amplitude and frequency. Of constant amplitude and frequency, these are produced. And these are termed as, these oscillations are LC oscillations. So these oscillations are LC oscillations. Or LC oscillations. Now I'll repeat all the steps once. Just listen it carefully if you have missed any of them. In LC oscillations, we have an inductor connected in series with a capacitor. That's why we say it's the LC circuit. So this is the first step. Here here the magnetic energy is 0, electric energy is high because your capacitor here is fully charged. This capacitor here, this is fully charged, whereas this is 0, right? So here what happens? capacitor is completely charged, whereas your inductor is at zero. So there is no presence of magnetic energy, but there is high presence of electrical energy. All right. Secondly, this was the first step. So what happened to the electrical energy? Electrical energy, this was high. Then you have second step. In the second step, what happened? The capacitor began to discharge itself. This is the discharge of capacitor which occurred in the second step. So there's a slight decrease in the electrical energy and slight increase in the magnetic energy. Because of the movement of current, motion of current, magnetic field lines have been produced. And if magnetic field lines are there, there will be associated half Li square magnetic field energy. Third point says what? Now the capacitor is fully empty because all the charge has vanished. So this is fully empty. Here, all the charge and the current have been converted into what? These are your magnetic field lines. So you just have high value of magnetic field, your capacitor is fully empty. Now there's a time to recharge the capacitor back. So recharging of the capacitor again. So that was your second step. This was your third. This was your fourth. So in fourth step, what happens? This is the recharging of the capacitor. So again, electrical energy, magnetic energy is now getting converted into electrical energy. What about the energy state of both of these? There will be a magnetic decrease in the magnetic energy. There will be an increase in the electric energy this time. And the fifth step, what will happen? Polarity will just become opposite. The rest of the things will be as the same. Now then what will happen further? Further steps will be same as above. Now again, discharging will begin, inductor will become charged, capacitor will become fully empty. Then when it will recharge, it will shift the capacitor's polarity back. And when the polarity is achieved back, then what happens? You have the initial state eventually with which you had started. This is what is meant by LC oscillations. Definition also I have written: when a charged capacitor is allowed to discharge through a non-resistive inductor, electrical oscillations of constant amplitude and frequency are produced, and these oscillations are called LC oscillations. L for inductor, C for capacitor. All right, note it down. Wherever you have doubts, ask me. We'll write the equation also for this.
Ma'am, this here LC oscillations are not there.
Yes, Zed, you were asking something?
Ma'am, LC oscillations is not there. Yeah?
Yes, LC oscillations we are discussing. LC oscillations. Because LC circuits we have discussed now. So LC oscillations we are discussing. Then we'll move on to transformers. One equation we'll discuss because second this linear differential equation is there. That we'll discuss and then we'll start with it.
Ma'am, can you show the second one again?
Yes, Khalid?
Can you show the second diagram again?
Yes.
Done, ma'am.
before we begin with the revision of questions, just one more. D square Q over dt square plus omega naught square Q is equal to 0. This is known as linear differential equation. Differential equation. So for half an hour, let us just revise from the previous topic. Yes, Khalid, I'll show you. Then we'll begin with the revision first, then we'll at the end we'll do the transformation.
Ma'am, can you show the fifth one now? Done, ma'am.
Try this question, class. So a graph has been given. You have to find out the root mean square value of AC. So no, do not use any formula. Use the definition of RMS that is given to you. By that, try to find out the value of AC. AC means alternating current. So calculate RMS value of the alternating current, which is shown in this paper. Try all of you once, then I'll discuss. It won't, the calculations are not tough. It won't take you so much time. See, how will you solve this question? This is the first value of current that you will get, I1. I1 will be equal to 2 amperes from you. I2 will be equal to minus 2 amperes. You can notice this is I2. And again, I3, the third value of current that you'll obtain, this will be 2 amperes. Now, if you look carefully, you have the values of current. Now the work of the graph is over. Now IRMS will be calculated by the formula of IRMS current that you have. When we were discussing IRMS and any root mean square value, I have told you first we'll square all the terms. So it will be I1 square, I2 square, and I3 square first. Then square done, then mean value. Mean value is taken by adding the numbers divided by the amount of or the numbers that you have, that is 3. And last step is taking the root value. So this is the formula of IRMS current. So what do we have? We have 2 square plus minus 2 whole square plus 2 square. This whole divided by 3. So what will it be? 4, 4 and 4 over here. So that will give you 12. 12 by 3 under root. So that is under root 4, which is equal to 2 amperes. So IRMS value will be 2 amperes. Like this, you have to solve this question. All right, note it down. First part is also at resonance, angular frequency of source at resonance. Now the angular frequency of the source at resonance. This is also at resonance. So angular frequency is formula we had seen, which we called if you multiply it by 2 pi, not multiplied, 2 pi nu. Yes, multiplied by 2 pi, that will give you the resonant frequency. So whose formula is under root LC. L is what? L is 50, capacitance is 18 to 10 to the power minus 6. So once you solve this, I think it will come out to be 50. Just check someone. I think the answer was 50 radian per second. Second is the current at the resonance. So somebody had answered also. I think it was Samira. Yes, Samira, your answer is right. Here we had to initially calculate the impedance for calculation. Now at resonance, we already know that impedance is equal to the resonance already. And sorry, not resonance, resistance at resonance. And resistance value is given as 40 40 ohm. So this will be what? This will be 40 ohms. So Z is equal to R, which is 40 ohms, and we have to find out IRMS. ERMS is also given as 240 volt. We have to find IRMS. So IRMS will be equal to ERMS divided by Z, which is equal to 240 divided by 40. This will give you 6 amperes. Fine, note down the solution. Then after 5 minutes, I'll start with the transformers. Then if time is left, then we'll do more questions. See class, let's start with transformers now. I hope you've written this part. Now transformers are what? Transformers are basically devices. These are electrical devices. I'll write down the definition as well. So transformer, it is an electrical device. This is an electrical device. So what does it do? It converts AC, which is at low voltage, into the one which is at high voltage, or alternating current that is present at high voltage to low voltage, either high to low or low to high. Depending on whether it is low to high or high to low, you have different types of transformers. But what's the function of a transformer? It converts the potential voltages, either low to high or high to low. So transformer is an electrical device for converting This is for converting an alternating current. So AC gets converted when at low voltage to high voltage or vice versa. Reverse can also occur, means if it is from high to low. Now see, if it increases the input voltage, increases means if it is from low to high, that is, it increases input voltage. Then that type of transformer, we call it as a step up transformer. Step up. You can remember step up by see something that is going up. So here what is going up? The voltage is going up. So from low to high, voltage has increased. The input voltage increases. It's from low to high. So that's why the name is given step up transformers. Then you step up transformers. Now, contrary to this, if high to low voltages are changed or it decreases input voltage, we call such type of transformers as step down. Now, why do we call it as step down? Because from high voltage, it is going back to the lowest position, or the input voltage is getting decreased. Fine. So there are different arrangements of transformer also, that's a different thing. But basic, you have step up transformers and step down transformers. Now, again, the principle of transformers you already know. We have already studied the principle of transformers. Remember, we studied this topic in under induction. Induction was categorized into two groups. One was self-induction, which was the induction that occurred within the coil due to change in the current of the same coil, as well as the change in magnetic flux of the same coil. That was self-induction. Within the same conductor, within the same coil, induction is occurring. If you had two coils, because of first coil, the other one got induced. That's what we called as mutual induction. So principle is just mutual induction. That if in one of the, or you can say the changing current is passed into any one of the coil, then induced EMF is set up in the other coil, the way we have studied it. So principle you have already studied. Principle is mutual induction. Mutual induction, you can say changing current is passed through two coils. So induced EMF is set up in the other coil. Now, construction involves two types of transformers that I was mentioning to you. One is the core type. Other one is the shell type. Fine, core type and the shell type. Now, how it is constructed? Let us see first the core type. Let's see. So, in the core type transformers, the primary and the secondary coils are separated. These are wound separately. I'll show you. Let's say this is this is the one side of the transformer, this is the second. So essentially what is there? A transformer essentially consists of two coils. Fine. This is the arrangement. What in actual is present? There are two coils which are insulated copper wires that are present. So different number of turns are present and this is a soft iron core. on this slab of iron core, turns of copper windings are done. So first one, this one is termed as the primary, and the other turnings are termed as the secondary. To which the electrical energy is supplied, you say the primary coil, and to which the energy is drawn, or you can say output one, that is known as the secondary. So to prevent energy losses, or there are eddy currents also we had studied in brief, laminated core we use. So laminated core is present. Basically, this is soft iron core. Here you have windings. So in core type transformer, what happens? The primary turnings are made like this. This is what? This is the primary. It has a number of turns. And regarding the secondary, on the other hand, this one, the output one, this is written as the secondary. So this type of arrangement, when it is there, we call it as the core type. Now, in place of a shell type transformer, like this, in case of shell type, this is how the soft iron core is constructed. And the primary wire is drawn on this. This red one is the primary. And the secondary one is also tied up on this one only. Like this. This is the secondary. Fine, this is what is shell type. So in core type transformers, what happened? Primary and secondary coils are wound on separate limbs of the core, so that the core is largely surrounded by the coils. And most of the modern transformers are of core type only, this one. In shell type includes what? In case of shell type transformers, primary and secondary coils are wound one over the other on the same limb of the iron. This is the same limb of the iron core. So coils are largely surrounded by iron core, which is the center of it. So TV transformers, radio transformers, these are mostly shell type transformers, but we use core type transformers more often. All right, this is what is the construction. Now the working. Okay, before we move on to working, I think then formulas also I'll introduce. Before that, just note it till here, then we'll move on to the formula. Formula for AC, this transformers are very easy. Number of turns you have to remember, voltage you have to remember, and current you have to remember. C class. Now the working of a transformer. So working of transformer is also not again new thing to you because you have already studied mutual induction. So I'll do one thing. I'll write down simultaneously. I'll explain you. Then only you read to understand. So alternating current will pass through where? It will pass through the primary first. All right. Alternating current will pass through the primary coil first. So as the alternating current, alternating, as the alternating current flows through the primary. What will happen? It will generate magnetic flux in the core, and this will pass through the secondary. So it generates alternating magnetic flux which passes through the secondary. So this passes through the secondary. Now what happens whenever there is a change in magnetic flux? What have we studied? Induced EMF will come into action. So because of changing flux, induced EMF is set up in the secondary due to change in magnetic flux. All these things are repeating. It's just that we have divided the passing and the passage of current into primary and the core of the coil and the secondary. Rest of the phenomena, all these you have studied in electromagnetic induction. Nothing is new over here. So due to change in what? Magnetic flux, due to change in the magnetic flux, there will be what? Induced EMF will occur in the secondary. So induced EMF will occur in the secondary, and also there will be a self-induced EMF in the primary also. Self-induced EMF will be there in the primary coil as well. Fine. Now, what will happen? Flux linked with each turn of the primary will be equal to flux with each turn of the secondary. So this is the basic principle. E is equal to minus d phi over dt. We have studied. From there, all these terms are introduced. Now, if I say induced EMF that is linked in the primary coil. So induced EMF that is linked in the primary coil will be what? Number of turns of the primary, then d phi over dt. This will be the formula of it. Right, class? So EP is what here? EP is the induced, or let me write induced. This is the voltage of the primary. EP is what? Voltage of primary coil. Here, just remember the symbols. This part is easy. The calculations is easy over here. So voltage of primary coil, NP is what? Number of turns of the primary coil. So number of turns of primary. Similarly, according to this formula, you will be having it for secondary as well that we have seen. So it will be ES is equal to minus NS d phi over dt. In certain books, you will find this as 2 written and primary is 1 written, like E1 is equal to minus N1 d phi over dt. E2 is equal to minus N phi and N2 d phi over dt. So everything is same. I write S and P usually to make it differential from whether it is primary or secondary. So this is voltage across secondary. This is number of turns of secondary. Now, if you will take the ratio of these two, what are you left with? That is the first formula you obtain. See, if you take the ratio d phi over dt, will cancel the d phi over dt. What are you left with? ES divided by EP is equal to NS divided by NP. This is the first formula. You can also write it as EP divided by ES is equal to NP divided by NS. But remember, whatever will be on the numerator for the voltage exactly will be for the number of turns. For current, you will see it getting reversed. I write down the formula of current also. Current is actually derived from here, from the power, from the output power remains the same. So it's E2 I2 is equal to E1 I1, or you can write it as ES IS is equal to EP IP. From here, you will notice that it is opposite. If you shift this, this will come in the denominator. ES can be written as what? ES can be written as EPIP divided by IS. From here, you can see ES and current is opposite. ES and current are opposite. So number of turns will be exactly whatever is in the numerator. If it's secondary above, here we'll write secondary. If it is primary above, for example, if the formula is EP divided by ES, so here we'll write NP divided by NS. That will be the formula. But in case of current, it is the opposite that will occur. So formula for current includes exactly the opposite. It is IP, means current in the primary coil, divided by current in the secondary coil. This is equal to voltage in the secondary divided by voltage in the primary, which is further equal to number of turns in secondary divided by number of turns in primary. Notice the difference. These two are same. This is opposite. So you can use any of these. You can even write NS by NP is equal to IP by IS. You can use these two as well. So whatever are suited, that we use. So this is actually the output EMF divided by the input EMF. Or one more thing, power also you can write, input power and output power also you can write from here. Input is what? Input is at the primary, and output it as the output is at the secondary. So power input will be what? Power input. This will be equal to see, power's formula is what? VI. So this will be equal to EP IP. And power output, this will be equal to VI ES IS. Fine. And you have coefficient of efficiency. You must have studied last year in, I think, thermodynamics in 11th, it is there. Efficiency of a transformer. Efficiencies of refrigerator are there. Beta, you must have studied. All these are included in your thermodynamics. So eta, the symbol is known as eta. This is actually the efficiency. This is written as power output divided by power input multiplied by 100. That gives you this gives you the percentage in terms of percent you calculate. So what exactly is this eta? This is the efficiency of a transformer. How much efficient is your transformer? For machines, we always have this. Refrigerators, Carnot engine, all these are there. So it's the efficiency of a transformer. So it's the efficiency. So these are certain formulas that you should be aware of. First formula is this one. this relation, this box is very important for the solving questions of on transformers. For transformers, questions are very easy. These are just directly based on this. Any relation will be used, one of the quantities will be unknown. Like out of all these three, rest of the things will be given, number of turns in the primary will be asked. Like this, it can be given. Secondly, you have to remember powers formula and efficiency. These three things you have to do. So any doubts in here, you can ask me. Start noting from here. Wherever you'll get stuck, ask me. I think from working, you have to note it down. Note it down. Class, this transformation ratio means means the number of turns in the secondary divided by number of turns in primary. That is given to you as 100. Transformation ratio, just in case. Transformation ratio is needed here. No? Yeah, this one. You can try this question, try the parts. This is a very easy question based on the formula. The class duration is for 2 hours. So I think 20 minutes are left now. After this question, most probably I'll stop with the class. So the class duration is for 2 hours. Yes, Z, first and second part are correct. Try the third and fourth part meanwhile. So it says that the primary coil of an ideal step-up transformer has 100 turns. So this is the number of turns in the primary. Okay, I'll explain. So number of turns in the secondary is, no, in the primary is given as 100. Right, and the ratio of NS by NP, the transformation ratio, this is known as the transformation ratio. This is given as, yes, that is right. Power 1 is also right. So NS by NP is given what? This is given as 100. Now number of turns in the secondary is unknown to you. So number of turns in the secondary will be what? This is solution for the first part. Number of turns in the secondary will be number of turns in primary multiplied by 100. That gives you 10 to the power 4 number of turns. Second part says what? Voltage across the secondary. So you can use this also. Voltage, any information about the primary? Input voltage is given 220. So input voltage means voltage in the primary is given as 220. And we need to calculate what? We need to calculate voltage in the secondary. So NS by NP is also known, which is 100. So what is unknown here? NS by NP will be equal to ES divided by EP. From here, ES will be equal to NS by NP multiplied by EP. That will give you 220 and then these two zeros. This much volt. Third part says what? Third part says current in the secondary. Current in the primary has not been given, no. Input voltages, ideal transformer, primary coil of an ideal transformer is given. See, we have to first calculate the primary one. For the second part Z, see, power is given to you. Power in the primary is given as 1100 watt. Right. So for the third part, what we'll do, we'll calculate the power. Power is given as what? 1100 watt. Okay, now try it. So power is given in the primary and EP is given, which is 220 volt. So from here, we'll calculate IP. Power is equal to potential into current. Potential into current. So for primary, everything will be primary. From here, you can figure it out. IP will be equal to power in primary divided by EP. So this is 1100 divided by 220. So that will give you 5 amperes. Now IP is known. Now you have all the values. You can put it into any of the formulas. So let's write NS and NP already because the ratio is given. So NS by NP will be equal to IP by IS. See, this is reversed for current. So what do we have to find? IS. IS will be equal to IP into NP by NS. So IP is 5 divided by NP by NS will be 1 by 100. No, it will be 0.005. No, see, this is 100. 0.05 amperes. This is NP by NS, which is 1 by 100. Okay, yes, 0.05, correct. And last part says what? Last part says power, no? Power in the last wala. Power in the secondary. So see, power in the secondary will be what? Power in the secondary is equal to voltage in the secondary multiplied by current in the secondary. Voltage in the secondary we had calculated 220 plus not multiplied by these two zeros, and IS is 5 by 100. So 0 will get cancelled. 5 into 22, this will be left now. This will be 1100. Or even you can do one more thing. Power, yes, power already is there, right? Power we have already obtained. 1100 watt is already good. And also for an ideal transformer, remember, for ideal for an ideal transformer, efficiency is 100%, then only you'll say, no, it's ideal. In reality, we do not have any material or any machine as ideal. But if you talk about an ideal situation, transformer's efficiency should be 100% without any wear and tear and loss of energy. So at that time, power input will be equal to power output. This also just remember this line. All right, class, note down the solution. Wherever you get stuck, ask me and text me done when you have written at the end. And I'll stop with the class.